Let me take a minute and discuss the kilovolt rating of the T-Rex 450S motor. I'm only going to use one example with the T-Rex 450, but you can extrapolate this information to different kilovolt motors and different voltage battery packs. So in the case of the T-Rex motor, it's a 3,550 kilovolt motor. And if we take the kilovolts and multiply it by a voltage, we'll get a free RPM of the motor. By free RPM in the motor, this is a philosophical RPM where there's no load on the motor. Actual flight RPMs will be considerably less. So I took 5 packs from my T-Rex and averaged the voltage, and they came out to 12.29. These are freshly charged packs. So if we take the kilovolt rating times the voltage, we get a free motor RPM of 43,630. Now, when we discharge that battery pack, I'm assuming the cells drop down to 3.2 volts. We have 3 cells, so that gives a discharge pack voltage of 9.6 volts, and the free RPM is 34,080. Now let's coordinate some of this information to the gear ratio in the T-Rex 450. The main gear is 150 teeth. And we have 2 options of pinions in the T-Rex 450, a 13-tooth pinion and a 12-tooth pinion. I prefer the 12-tooth pinion for 3 reasons. First of all, the teeth in the stock pinion are cut beautifully with the 12-tooth pinion, and in the 13-tooth pinion, the teeth are just boxy. They're just not cut right. But I have other more important reasons for using the 12-tooth pinion. Another reason is that I don't want the high rotor RPM that the 13-tooth pinion provides. A rotor RPM that high is not necessary, and I don't think it's needed. And one of the reasons that the guys are running the 13-tooth pinion is they're not using any program mix. So they need a high rotor RPM so when they put in a large cyclic deflection that the rotor RPM doesn't suck down too much. Well, we're going to use program mix, and so we don't have to worry about the rotor RPM sucking down. So the 12-tooth pinion gives a moderate, more efficient rotor RPM for the motor and the battery pack, and you'll get longer flight times with a 12-tooth pinion. There's one other reason I like to use the 12-tooth pinion, and it's because that the 12-tooth pinion has more torque than the 13-tooth pinion, and here's why. If we take the number of teeth in the main gear and divide it by the teeth in the pinion, we get a ratio. In the case of the 13-tooth pinion, it's 11.5 to 1. That means that for every 11.5 times that the motor goes around, the main rotor goes around once. In the case of the 12-tooth pinion, every 12.5 times the motor goes around, the main rotor goes around once. Now, because the motor is spinning a little bit faster in relationship to the actual rotor RPM, the 12-tooth pinion is going to have more torque, so that when we put the cyclic load into the rotor system, the program mix and this gear ratio is going to compensate better for that cyclic load. Now, another option that we have here is to replace the stock T-Rex 450 pinion with an aftermarket pinion. And this pinion is made by Revco, and it's distributed by ReadyHeli.com. This is a beautiful piece. The teeth are shaped just perfectly on this thing. And again, they make it in 12-tooth pinions, 13-tooth pinions, and so this is an option that I would really recommend that you upgrade to when you build your T-Rex 450. In the next figure, let me go ahead and coordinate these free RPM numbers and these gear ratios to actual rotor RPM numbers. Here's the graph that shows everything in plain, simple rotor RPM terms. First of all, from the other diagram, on the horizontal line, we have battery voltage and motor RPM. So here's a freshly charged pack at 12.29 volts at a motor RPM of 43,630, and a discharge pack of 9.6 volts with a motor RPM of 34,080. On the vertical line we have rotor RPM, and then here is a line that signifies the 13-tooth pinion with the gear ratio of 11.5 to 1. This is not to scale, this is just a slope that shows that we're starting with a charged pack and ending with a discharged pack. Here's the line for the 12-tooth pinion with a gear ratio of 12.5 to 1. For this 13-tooth pinion, when we start out, we've got 3,794 rotor RPM, and at the end of the flight, we have 2,963 rotor RPM. For the 12-tooth pinion, we start out with 3,490 RPM, and we end up with a rotor RPM of 2,726. It's interesting to note that the difference between the starting RPM and ending RPM of the pinions is different. For instance, with the 13-tooth pinion, the rotor RPM changes 831 RPM from the start of the pack to the end of the pack. With the 12-tooth pinion, the rotor RPM only changes 764 from the start to the end. So that's just another reason why I like the 12-tooth pinion. When I say electric helicopters, what do you think about? I think about electronics and electricity. And electricity means wires. And wires mean connectors. And connectors mean soldering. So the first thing I have to teach you how to do is solder. You'll need to solder the connectors to your battery packs, which is probably the most dangerous part of building an electric helicopter. Then you'll have to solder the connectors to the speed control, ESC, solder the connectors to the motor, and then solder up the connectors for the adapter cords between the charger and your battery pack. Now, soldering isn't that hard, particularly if you have the right tools. You'll need a soldering iron between 25 and 30 watts. Make sure that it has a flat tip. I went to Radio Shack to buy a soldering iron, and they only sold soldering irons with pointed tips, so you might want to go somewhere else when you buy your iron. While you're buying the iron, buy a stand for it. It's great to hold the hot iron so that you don't burn down your shop. Also, pick up some solder. This is 32 thousandths in diameter, and it's a 60-40 combination of tin and lead. I bought it at Radio Shack. Finally, one thing that I wish I would have bought years ago is this Helping Hands with magnifier. Now, I didn't need the magnifying glass, I took that off, but this is made by Cronus, and I got it at Radio Shack. The beautiful thing about it is it has a nice, heavy metal base, and it's perfect to hold the wires and connectors as you solder. Now, as you can see, I've made some modifications to it. Let's take a little closer look at those changes. The unit comes with a metal bar, and at each end of the bar you'll get a little attachment clip that has an alligator clip. The problem is that the alligator clips are too far apart and they have to angle together to get the kind of spacing that we need for our soldering. So the solution to that is to use a custom piece of wood, and the wood is mainly rectangular so that the little thumb screw bites into the side of it. And then I can put both attachments on one side of center. This gives me nice close spacing. Then what you want to do is remove the alligator clips and modify a clothespin. Just fashion a little rectangular piece here on one end, and then you can pull out the alligator clip. You can slip in the clothespin and use the little thumb screw to tighten it down, and this will give perfect spacing for our wires and connectors. In terms of connectors, I've worked with two types. This is the E-flite connector, and it's a really nice connector and reasonably priced. It's keyed so that you can only plug it in one way, and it fits nice and tight. And then to pull it apart, it has nice ribs on the connector so that you can grab the ribs and pull it apart. Your other option is the Astroflight connector, and it's called the zero loss connector. Here you can take a look at the ends, and then the Astro connector plugs in like this, and then to disconnect the Astro connector, it works best if you just pull the wires to pop it apart. Now, when you solder up the Astroflight connectors, this connection needs to be slipped on the wire before you solder the wire to the connector. On the other hand, the E-Flite connector, you solder up the wires to the pins and then slide the housing on after the pins are soldered up. To teach you how to solder, we're going to wire up the ESC, or the speed controller. Now, to save some time, I've already soldered the connectors on the end. These connectors go to the motor, and they are female. The connectors coming off of the motor are male. Notice how I'm not using a connector block here. It's just easier to plug in and unplug these wires if they remain independent. What I'm going to do is show you how to solder up the lead that goes to the battery pack, and I'm going to use Astroflight's zero loss connectors. They have a rounded end so that there's no problem with getting the wrong polarity. And the easy way to remember which goes where is that the red wire goes through the rounded end. And because this is the zero loss connector, I have to slide this on before I solder on the pin. If this is the E-Flite connector, you can solder on the pins and then just push the body on later. To get a good soldering joint, it's most important that you heat up the connector before you apply the solder. The connector must come up to temperature. Never ever take the solder and touch it to the iron to get things hot to flow into the connector. You have to wait until the connector comes up to temperature. Now, you can take the bare tip of your soldering iron and put it on the connector, but when you do that, there's very small contact area. So it takes a long time for the soldering iron to heat up the pin. What I like to do is just put the slightest amount of solder on the iron, and then when I put that onto the connector, the heat transfer will be much better. So there I've put just a touch of solder on, and now I'm going to just wait until the pin comes up to temperature. I can check the temperature every once in a while just by laying the solder in, and things are coming up to temperature here. Also, this piece of wire was tinned. It was soaked with solder before I put it into the pin. Now we've got good temperature. Fill it with solder. Go ahead and remove the iron and allow everything to cool. You can see how we have just a touch of solder on the pin. You can take a file and just sand off the solder. Again, if you take away a little bit of the gold plating back here, it doesn't make any difference, but you want to make sure that the gold plating stays perfectly intact on the pin itself. With the pins soldered to the wires, go ahead and pull the pins back into the housing, and then the easiest way to seat the connectors is to go ahead and take the battery pack and just plug it in and go ahead and push firmly. Again, with the Astroflight connectors, then you want to pull on the wires to pop the plug, because sometimes if you pull on the housing will come off of the pins. The pins aren't a real tight fit in the connectors. Now I've soldered both connectors onto the battery. Like I said before, this is one of the most important critical parts in building an electric helicopter. This pin must always be insulated. I've used heat shrink tubing here. You can use fuel line, anything so that the two connectors do not touch. If they touch, you're going to get smoke, maybe a fire. You'll probably ruin the battery pack. So again, this is very, very critical. Wiring up the connectors isn't that big a deal, but then the question is, how do you get the connectors into the housing without the connectors touching? Well, to do that, I use a plastic ruler. You could use a credit card or something like that. And I hold the plastic ruler in between the two pins, and then as I pull the pins into the housing, the ruler keeps the two pins separated. And so there goes one, and it slid into the housing. Now I can remove the ruler and wiggle the second one around so that it goes into the housing, and there I've successfully got both pins into the housing. To build an electric helicopter, you have to have a heat gun because you have to shrink the heat shrink tubing onto the connectors. This is Dubro 3/16 inch heat shrink tubing, and the process is the same for a male or a female connector. I'm just showing a female connector. What you want to do is push the heat shrink tubing over the connector so it overlaps about 1/2 millimeter. And then when you hit it with the gun, the heat shrink will come and shrink right down flush with the end of the connector. Let me take a minute and build a foundation for you for LiPo batteries, and then in a minute we'll take a look at LiPo chargers. First of all, a single LiPo cell is 3.7 volts. Memorize that number. When the cell is discharged, its voltage drops down to 3.2 volts. Memorize that number. Now, some people may say that you can discharge a LiPo cell to 3 volts or 2.9 volts, and all that I'm going to tell you is that 3.2 volts is a safe, conservative number where you're not going to do any physical damage to the cell. Now let's look at these cells wired up in series. And the way that I remember series is that the ends are swapped. So here's a positive end here, and then we swap the end. It's positive down here. If you take 3.7 volts and 3.7 volts, that will give us a total of 7.4 volts. And here's a 2-cell pack from the Blade CX2, and it is 7.4 volts. Now, if we take 3 cells and add 3 cells, we get 3.7 and 3.7 and 3.7, which gives us 11.1 volts. And again, here's the pack from the CP Pro, and again it says 11.1 volts. Now, these packs are relatively small. They're only 800 milliamps. And so when we charge any LiPo pack, it can't be charged at a greater rate than its capacity divided by 1, or the C1 rate. So in the case of this pack, that's 800 milliamps divided by 1 is 800 milliamps, which is exactly the same thing as 0.8 of an amp. Now, if we take a larger pack, it's 11.1 volts, and so we know that it's a 3-cell pack, but it has a greater capacity, 2100 milliamps. And so 2100 milliamps divided by 1 is 2100 milliamps, or 2.1 amps. So we can't charge this pack for the T-Rex 450 at any greater than 2.1 amps. Now, if the cells in the pack become discharged lower than 3.2 volts, we have to bring the voltage up to 3.2 volts slowly. And we do that at the C divided by 10 rate, or it's sometimes referred to as the C10 rate. So, in the case of the smaller pack, 800 milliamps divided by 10, we drop the 0, and this pack would have to be brought up slowly at 80 milliamps until all the cells are at 3.2 volts or above, and then we can charge it at 800 milliamps or 0.8 of an amp. And the same thing for the T-Rex 450 pack. C divided by 10, or the C10, 2100, drop the 0. We would trickle this pack at 210 milliamps. When the cells come up at or above 3.2 volts, then we can charge it at 2.1 amps. Now, these packs are referred to as 3S packs, meaning that all of the cells are wired in series. Sometimes you might even see 3S1P, meaning that it's a single pack in parallel. But normally, one pack in parallel, it really makes no sense, so the 1P is dropped, and you'll even see the S dropped, so that if you have a simple 3S pack, it's simply referred to as a 3-cell pack. Now let's take a look at these packs wired up in parallel. From the previous example, I'm going to start with a simple 2-cell pack. That pack is represented by 2 cells. That's why this battery is split, represents 2 cells, and the milliamperage is 800 milliamps. When we wire something in parallel, it means all of the cells are perfectly lined up. So that means we go plus to plus and minus to minus. When we do that, the overall voltage stays the same. So this pack is 7.4 volts, and when I put 2 of these packs together in parallel, it's 7.4 volts, but the capacity doubles from 800 milliamps to 1600 milliamps. 1600 milliamps can also be referred to as 1.6 amps. Now, the terminology for this battery pack is a 2S, because each pack has 2 in series, and we have 2 packs in parallel. So, a 2S, 2P. Taking the example to the next level, now I've got a 3-cell pack, 1, 2, 3, 3 cells,